Assalamu alaikum. Assalamu alaikum, students. There is another lecture of course title Particle Physics, course code PHY654. Today's lecture is Dirac equation. In this lecture, we will briefly discuss why we use Dirac equation in particle physics. In previous lecture, we have discussed about Klein-Gordon equation. So in this lecture, we have briefly discussed the Klein-Gordon equation, its impact in particle physics. Now the question arises, why there is the need to use Dirac equation in particle physics? All these things will be covered in brief in this lecture. Let us start our topic. There is the slide that you can see highlights of the previous lecture. As we discussed in previous lecture about Klein-Gordon equation, we have started our previous lecture from the Schrödinger wave equation. We discussed why we cannot use the Schrödinger equation in particle physics. There are some reasons behind this that we cannot use the Schrödinger wave equation in particle physics. Now we suggested that there is another equation that is known as Klein-Gordon equation that can be used as that can be used widely in particle physics to study the structure of the composite particles. We have discussed the second order time derivative in the Klein-Gordon equation. This operator, that is D'Alembert operator, we have derived this in previous lecture, is responsible for both the negative energy plane wave solutions and the misbehaving probability density. Actually, in previous lecture, we have a look at the problems relevant to the Klein-Gordon equation. There are the main problem with Klein-Gordon equation that it gives the negative energy plane wave solutions, and also the probability density is also very disturbing in Klein-Gordon equation. So we cannot use Klein-Gordon equation. Basically, it is sometimes said that Schrödinger discovered the Klein-Gordon equation before the equation that is on his name, that is the Schrödinger equation. But then he rejected this equation because this equation was quadratic in curly by curly t. In last lecture, we have seen how the Klein-Gordon equation give us the negative energy and also the negative probability density. That was the major problem. The probability density can never be negative, but in Klein-Gordon equation we have seen there is the negative probability density problems. That is the big issue of the Klein-Gordon equation. In 1928, an attempt was made to solve out this problem. Lorentz invariance requires such a wave equation to be linear. The Dirac found that there was the equation that described particles with spin 1 by 2, just as we required the equation for electrons. Dirac also predicted the existence of the antiparticle. That was the also idea that wasn't taken seriously until 1932 when Anderson discovered the positron. So basically there are some major problems associated with Klein-Gordon equation that inspired the Dirac to suggest the another equation that was like Schrödinger equation and also contained only first order time derivatives. Here you can see probability density equals to iota square bracket psi steric curly psi by curly t minus curly psi steric over curly t into psi bracket closed, and E can be written as E is equal to plus minus square root p square plus m square. In upcoming slides, we will also review the problems that was associated with Klein-Gordon equation. Before going to the detailed description of Dirac equation, here we are reviewing the issues with the Klein-Gordon equation. Klein-Gordon equation was basically obtained in 1927 by Oscar Klein and Walter Gorton and named as Klein-Gordon equation. There are certain problems that arises which stand in its way of being a complete description of the dynamics of the relativistic electrons. So basically there are the list of the problems that are associated with Klein-Gordon equation that inspired the Dirac to suggest the Dirac equation. As we know that Lorentz Klein-Gordon equation is Lorentz covariant, but in particle physics we require equation that is Lorentz invariant. Also, it fails some of the requirements of the quantum mechanics postulates. Basically, it fulfilled the postulates of special theory of relativity in very good way. But there are some requirements of the quantum mechanics postulates that wasn't followed by the Klein-Gordon equation. As we know that we have derived the Klein-Gordon equation in previous lecture, and we found that it is the second order differential equation with respect to time. Unlike the Schrodinger's equation of quantum mechanics, we are now that Schrodinger equation is first order differential equation. But here is another problem with Klein-Gordon equation, that is that it is the second order differential equation with respect to time. Being second order in time, determining a particular solution required information about both psi as well as psi by curly t. But quantum mechanics says wave function must be a complete description. So this is the major problem that arises due to the fact that it is the second order differential equation in time, that when we want to determine the particular solution of any system, we need required additional information about psi and curly psi by curly t. But as the students of physics, we know that in quantum mechanics, wave function psi contains the complete information about the system. This is very big failure of the Klein-Gordon equation, that we also require the additional information. Also, Klein-Gordon equation admits solution where norm and hence probability is not conserved. As we know that in quantum mechanics, we said that the probability density is mostly conserved, but the Klein-Gordon equation accept the solutions that are norm, and so due to this problem our probability is not conserved. So we can say that Klein-Gordon equation is necessary but not sufficient. Means to say that their changes or new equations can be suggest that will be sufficient. Means that can make our way easy and good. So we can conclude that Klein-Gordon equation must be varies with some and other equation. There is another outline of the Klein-Gordon equation problems. It was actually found by Schrodinger before his non-relativistic equation. Here the non-relativistic equation is the Schrodinger wave equation. Before the discovery of the before the formulation of Schrodinger equation, that is the non-relativistic equation in quantum mechanics, this equation was suggested by Schrodinger equation. So Klein-Gordon equation is the relativistic generalization of Schrodinger equation, and thus it may be written in covariant way. As in previous lecture we have discussed in briefly that Schrödinger equation is the non-relativistic equation, and this equation was formulated and in the relativistic generalization, or the made the equation that follow the postulates of the special theory of relativity. So Klein-Gordon equation is basically the relativistic generalization of Schrödinger equation, and it may be written in coherent way, means to say that this equation must be written in coherent way for, as it was the co-fellow of the Schrödinger equation, that is the non-relativistic equation. Also, as we discussed in previous slides, that it is the second order differential equation with respect to time. So it didn't work for the hydrogen atom. It was also the major fault of this equation that it is the equation for particle having zero spin. For particles like electron or proton that have spin 1 by 2, this equation didn't work properly. Another major fault of this equation is that it is incompatible with the statistical interpretation of psi r square. As we know that the probability density can be found by using psi r square, but it doesn't work compatible with this statistical interpretation of psi r square. That is the major problem of the Klein-Gordon equation. Also, another problem of Klein-Gordon equation, it doesn't lead to a positive definite probability density, and also admits the positive and negative energy solutions. Means to say that there is the no definite positive value for the probability density, and also positive and negative energy solutions. Due to these features, there is the big blunder for in quantum mechanical theory, that we cannot take it equation relativistic equation. So we can also say that due to the negative and positive energy solutions, the arbitrary large energies cannot be extracted from the system if external perturbations lead to transition between positive and negative energies. Obviously, when there is the possibility of the positive and negative energy solutions, large energy cannot be extracted from the system. So we can summarize it as Klein-Gordon equation is necessary, not sufficient, and we cannot accept this equation as the equation of motion of particle with spin angular momentum. So Dirac's strategy was to find first order equations still compatible with relativistic energy momentum relation. These are the major problems with Klein-Gordon equation that inspires the Dirac strategy to form a good equation. Now we will discuss about the Dirac's insight. Basically, Dirac placed emphasis on two constraints. These are the two major points of the Dirac that he used to form the Dirac equation. Number one, relativistic equation must be first order in time derivatives. This is the major point of the Dirac equation. As we discussed, the Klein-Gordon equation is second order differential equation. Second point is that elements of the wave function must obey Klein-Gordon equation. It is the second major point that the elements of the wave function for Dirac equation must obey Klein-Gordon equation. So we need an equation that was both first order in time as well as space. This is the major achievement of Dirac equation that he used to form the equation. It was also suggested by the Dirac that this might be possible if we interpret the square root in the Einstein formula differently. That this is the suggestion made by the Dirac, that if we take the square root in the Einstein's formula differently, we can achieve the first order differential equation in time as well as space. Now we will discuss the significance, among other which is Dirac equation accounted for spin, discovered experimentally in 1925 but without a theoretical basis at that time. Dirac theory also predicted an antiparticle for every particle. Basically, it was also predicted after the suggestion of Dirac equation that there was the existence of antiparticle for every particle. Second one point, that Dirac equation is preferably used or can also be preferably used for the particle having spin 1 by 2. But as we noted in Klein-Gordon equation, that this equation was used only for spin 0 particle, but Klein-Gordon equation can also be used for spin 1 by 2 particle. So starting from the highlights of the previous lecture, we have discussed problem related to the Klein-Gordon equation. Then we discussed how the equation Polydirac discovered the Dirac equation. Now we are going to discuss in detail the Dirac equation. The classical Hamiltonian is quadratic in momentum. Dirac's cite for a Hamiltonian that is linear in momentum. Basically, as we know that the classical Hamiltonian is not linear in momentum, rather it is quadratic in the momentum. But Dirac suggested that Hamiltonian that is linear in momentum. This is the big difference of the Dirac equations Hamiltonian from the classical Hamiltonian. We can write the Dirac Hamiltonian as H is equal to alpha dot P plus beta m. This is our equation 1. Here P is the momentum and m is the mass of the particle. Here alpha equals to alpha 1, alpha 2, alpha 3 and beta are the coefficients. In order to satisfy the relativistic relation between energy and momentum, we must have any eigenvector with momentum p of h that. So equation 2 can be written as h square psi that is equal to p square plus n square p minus p raised to power minus 2 plus n square into psi. This is our equation 2. What should H look like such that these eigenvectors exist? So the Dirac suggests the Hamiltonian as H square that is equal to summation alpha I pi plus beta m into summation j alpha j pj plus beta m. This is the Hamiltonian. By squaring the equation 1, we get this equation. We have equation 1, H is equal to alpha dot P plus beta m. We take the square of the first equation H square and now we get it as H square is equal to, now multiplying both terms, we have summation ij alpha I alpha j pi pj plus summation I alpha I beta pim plus summation I beta alpha I pim plus beta square m square. Further simplifying this equation, we have summation I alpha I square p I square plus summation I is greater than j, taking common pi pj alpha I alpha j plus alpha j alpha I plus summation I alpha I beta plus beta alpha I pim plus beta square m square. Basically in equation 3, there is the equation above equation 3. In that equation, we have written the first term as for in two further terms. We have resolved summation I j alpha I alpha j pi j as summation I alpha I square pi square plus summation I greater than j ai alpha I alpha j plus alpha j alpha I pi pj. So we have basically resolved first terms in further two terms. Now we have four terms in equation 3. First equation for first term summation I alpha I square pi square, this is equal to 1. Summation I greater than j alpha I alpha j plus alpha j alpha I pi pj, this goes equal to 0. Similarly, summation I alpha I beta plus beta alpha I pim equals to 0. And the last term, that is beta square m square, this is equal to 1. So first and fourth terms have value of 1, while second and third terms goes equal to 0. This is our equation 3. So we can get equation 2 as in previous slide we have defined about the Dirac equation. In Dirac equation, we have defined the two coefficients that are alpha and beta. Now we can find out that the coefficient must satisfy the following requirements. These requirements are as below. There are the 2 points. You can say there are 2 points that must be followed by the coefficients in order to fulfill the requirements. Number 1, alpha 1 square, that is equal to alpha 2 square equals alpha 3 square equals beta square. These 4 coefficients and their squares must be equal to 1. Means to say that if we have alpha 1 square and alpha 2 square and alpha 3 square and beta square, these are all coefficient will be equal to 1. This is the first requirement that must be followed by the coefficients. Second one point is that alpha 1, alpha 2, alpha 3 and beta anti-commute with each other. Means to say that there is the relation of anti-commutation relation between these coefficients. If we have alpha 1, alpha 2, alpha 3 and beta, the second requirement that must be followed by the coefficients is that alpha 1, alpha 2, alpha 3, beta anti-commute with one another. So basically if we define out the values of alpha and beta, the alpha and beta cannot be ordinary numbers. Means to say that we just cannot assign the numbers to the alpha and beta. Likewise, we cannot assign alpha 5 value or beta 3 value like any other number. So we can conclude that alpha and beta cannot be ordinary numbers. So they are the matrices that act on a wave function, that is a column vector. Basically, if we want to find out the values of alpha and beta, we cannot say that they are ordinary numbers. They are basically the matrices that act on a wave function, that is a column vector. Basically, we will write the alpha and beta coefficient in form of the matrices. These matrices act further on by act on the wave function. Second thing is that it can be shown that the lowest dimensional matrices that have the desired behavior are 4 by 4 matrices. Previously we have defined that alpha and beta are not the ordinary numbers, but we want to write these matrices in form of the matrices. We will write alpha and beta in form of the matrices. These matrices are act upon the wave function and give us the further simplification. So these are the lowest dimensional matrices that have the desired behavior, that is the 4 by 4 matrices. So basically still we have defined what are the coefficients and what are the requirements that must be followed by these coefficients, and how we can define or nominate the values to these coefficients. Dirac Pauli representations. Now we will define the representation of these matrices alpha, these coefficients. As we discussed earlier that we will write the alpha 1, alpha 2, alpha 3 and beta in the form of the matrices. Now we will discuss about the Dirac Pauli representations of these coefficients. So alpha will be written as 2 by 2 matrix as 0 sigma. Second row will be written as sigma 0. Similarly beta will be equal to first row 2 by 2 matrix, and first row of the matrix will be I0. Second row will be 0 minus I. This is our equation 4. Now in previous equation 4 we have defined alpha as alpha is equal to 0 sigma 0. As we know that there are alpha 1, alpha 2, alpha 3. So sigma is the Pauli matrices. Now we will define what are the value of the Pauli matrices, or how we can nominate or define the Pauli matrices, and what are the nominations or representation of the Pauli matrices. Equation 5 will declare about the representation of the Pauli matrices. Sigma 1, that is equal to basically Pauli matrices sigma, that is equal to sigma 1, sigma 2, sigma 3, consist of 2 by 2 matrices. First of all, we will define sigma 1, that is equal to, first row will be write as 0 1, second row 1 0, sigma 2, first row 0 minus I, second row I 0, sigma 3, that is equal to first row 1 0, second row 0 minus 1. So equation 5 basically define the representation of Pauli matrices, that is included in assigning the matrices of the alpha coefficient. It must be noted that Pauli matrices are also traceless and Hermitian, and they also anticommute as well. As we defined earlier, alpha 1, alpha 2, alpha 3, beta anticommute with each other. Similarly, Pauli matrices that we have defined in alpha coefficient also anticommute with each other. So this is the Dirac Pauli representation. Now we are going to define the covariant form of the Dirac equation. We have discussed briefly about what is the Dirac equation, why we now need Dirac equation, as we have already Klein-Gordon equation. Now we have in previous slide we have discussed about the Dirac representations of the matrices of alpha beta coefficient. Now the upcoming topic that we are going to discuss is the covariant form of the Dirac equation. As we discussed in relativistic equations, we will define the 4 vector notation. In 4 vector notation, we have covariant and contravariant form. In this lecture, we will discuss the covariant form of the Dirac equation, like how we can derive our Dirac equation in covariant form. As we know that we had H psi, that is equal to alpha dot p plus beta n psi. This is the simple representation of the Dirac equation that we have described in our previous slides. Now we will replace H as iota curly by curly t and P as minus iota del. In first equation, putting the value of H and P as iota curly by curly t and P as minus iota del, we have equation 6 as iota curly by curly t psi that is equal to minus iota alpha dot del plus beta m psi. This is our equation 6. Now we will multiply equation 6 from the left side by beta. Note that as we discussed in our previous slide, we said that the coefficients of the Dirac equation must satisfy the relation that alpha 1 square, alpha 2 square and alpha 3 square beta square equal to 1. So using this notation, we have iota beta curly by curly t psi that is equal to minus iota beta alpha dot del psi plus m psi. If we further simplify this equation, we have iota beta curly by curly t psi plus iota beta alpha dot psi minus m psi that is equal to 0. Now we will expand the alpha as alpha 1, alpha 2 and alpha 3, and we will simplify our equation as iota beta curly by curly t psi plus iota beta alpha 1 curly by curly x plus iota beta alpha 2 curly by curly y plus iota beta alpha 3 curly by curly z psi minus m psi. This is our equation 7. Now we will use the 4 Dirac gamma matrices to solve out our equation 7, and we will expand our equation 7 as sigma gamma mu that is equal to beta beta alpha and gamma mu that is equal to gamma 0 and gamma. Here our gamma vector will be represented as gamma 1, gamma 2, gamma 3. So gamma mu that is equal to gamma 0, gamma 1, gamma 2, gamma 3. Comparing equation 7 and equation 8, we will write the wave equation in simple form. Iota gamma 0 curly by curly t plus iota gamma vector dot del minus m into psi that is equal to 0. That will be written as iota gamma 0 curly's mu minus m into psi that is equal to 0. This is equation 9. Equation 9 is called the Dirac equation. Now our psi is the 4 element vector. We said that psi wave function is a 4 element vector. We call it a bispinor or Dirac spinor. In next lecture, we will define the solutions of the Dirac equation have 4 degrees of freedom. How we can find the 4 degrees of freedom? There are the spin up and spin down solutions for a particle and antiparticle. One solution for particle spin up and spin down. These are the 2 solutions, and corresponding for antiparticle we have 2 solutions correspond to spin up and spin down. So basically this is all about covariant form of the Dirac equation. We have iota gamma mu curly mu minus m psi is equal to 0. We have derived this equation in previous slide, that is the covariant form of the Dirac equation. Basically this Dirac equation is set of 4 coupled differential equations. How it is the 4 coupled differential equations? For j is equal to 1, 2, 3, 4. We have, if we expand our previous equation in the form of summation, we will write it as summation k is equal to 1 to 4 square bracket summation mu is equal to 0 to 3 iota gamma mu jk curly mu minus m chronicle delta jk into psi k that is equal to 0. Or if we want to define the matrices, iota gamma mu matrix curly mu minus And now we will define the matrix for the chronicle data, that 4 by 4 matrix. First row will be written as 1 0 0 0. Second row 0 1 0 0. Third row 0 0 1 0. Fourth row will be written as 0 0 0 1 dot m. And now we have defined that psi is the 4 element vector, and we will write it as the column matrix psi 1, psi 2, psi 3, psi 4, that is equal to 0. We have defined the Dirac equation in the form of 4 coupled differential equation. Now we are going to discuss about the Dirac gamma matrices. We have defined that in previous slides we said that alpha and beta will be written in the form of the matrices, not in the form of numbers. If we want to represent the alpha beta coefficient, we will use the matrix notation instead of the numbers. Now we are going to discuss the Dirac gamma matrices as alpha is equal to 2 by 2 matrix. First row 0 gamma sigma, second row sigma 0, and beta will be written as 2 by 2 matrices containing first row I0, second row 0 minus I. As we defined in covariant form of the Dirac equation, gamma mu, that is equal to gamma 0, gamma 1, gamma 2, gamma 3. For gamma 0 we will simple write beta. Gamma 1 will be correspond to beta alpha 1. Gamma 2 correspond to beta alpha 2. Gamma 3 correspond to beta alpha 3. So this is the gamma mu notation. Now we will define the gamma matrices as gamma 0 will be equal to first row I0, second row 0 minus I. Similarly, gamma I, that is equal to first row 0 sigma I, second row minus sigma I 0. So we have also defined the gamma in the form of the matrices. Now we are going to discuss the gamma matrices in full matrix form, that are 4 by 4 notation of the matrices. Gamma 0, that is correspond to beta, will be equal to first row 1 0 0 0, second row 0 1 0 0, third row 0 0 minus 1 0, fourth row will be 1 0 0 minus 1. Gamma 1, that is correspond to beta alpha 1, will be equal to first row 0 0 0 1, second row 0 0 1 0, third row 0 minus 1 0 0, fourth row will be minus 1 0 0 0. Similarly, we will define gamma 2, that is correspond to beta alpha 2 as first row 0 0 0 minus I, second row 0 0 I 0, third row 0 I 0 0, fourth row minus iota 0 0 0. Gamma 3 correspond to beta alpha 3 will be written as 4 by 4 matrix form as first row 0 0 1 0, second row 0 0 0 minus 1, third row minus 1 0 0 0, fourth row 0 1 0 0. So this is all about Dirac gamma matrices. तो 11 to 12 30 हम लोग कर लेंगे. As for we have discussed that alpha beta coefficients will be written in the form of the matrices, neither in the form of numbers. We have defined the matrices in previous slide. Now we are going to discuss the properties of the Dirac gamma matrix. So we have a look at the properties of the Dirac gamma matrices. To find what the gamma mu, we have mu is equal to 0, 1, 2, 3 objects are. We multiply the Dirac equation by its conjugate equation. For the multiplication of the Dirac equation by its conjugate equation, we have gamma dagger multiplied by minus iota gamma 0 curly by curly t minus iota gamma dot del minus m multiply by iota gamma 0 curly by curly t plus iota gamma dot del minus m into psi that is equal to 0, and demand that this be consistent with the Klein-Gordon equation. By using this, we have following conditions that will be must followed by the gamma mu. First identity that will be followed by the gamma mu is gamma 0 square, means to say that gamma 0 square equals to 1. Similarly, gamma I square that is equal to minus 1. Here 1 shows the identity matrix. In equation 1, on the right side of the equation we have 1, that means the identity matrix. Second property is anti-commute, that is gamma mu, gamma v plus gamma v, gamma mu that is equal to 0. For mu is not equal to v. This is the second property of the identity matrix. Second property shows the anti-commute property for the gamma matrices. Here you can see there is the gamma I matrix. Here I has the value 1, 2, 3 so on. Similarly, mu and v have the values 0, 1, 2, 3. So this is the properties of Dirac gamma matrices. We have defined these matrices for alpha, beta, and also discussed these matrices in the covariant form of the Dirac equation. Starting from the properties of the Dirac gamma matrices, we have still defined the two important properties of the Dirac gamma matrices. First property is about identity matrix, that is gamma square that must be equal to 1. Second property shows the anti-commutation relation. Now we are going to define the third property of the Dirac gamma matrices, that is the gamma 0 dagger must be equal to 0. Means to say that if we take the conjugate of the gamma 0, these two values must be equal to one another. Similarly, b dagger equals to beta dagger equals to beta. This is the Hermitian conjugate of beta must be equal to beta. This is third property. Fourth property is that if we have gamma iota and I and we have dagger like gamma I dagger, it must be equal to beta alpha I dagger and whole dagger. And if we apply separately and open the relation beta alpha I dagger, it must be equal to alpha I dagger, beta dagger that is equal to, as we know that alpha I dagger equals to alpha I, similarly beta dagger equals to beta according to third property of the Dirac gamma matrices. So we have alpha I beta that is equal to minus gamma I. This is the fourth property. Then the relation gamma k gamma 0 that is equal to 0 shows that we have, if we have gamma k multiplied by gamma 0, it must be equal to minus gamma 0 gamma k, that is equal to gamma 0 gamma k. This is the fifth property. So we can also define it as gamma 0 gamma k gamma 0, that is equal to gamma 0 square gamma k dagger, that is equal to gamma k dagger. So we can also summarize the fifth property as gamma mu dagger must be equal to gamma 0 gamma mu gamma 0. If we want to define the sixth property in words, we can define it as in word. This means that we can undo a Hermitian conjugate gamma mu dagger gamma 0 by moving a gamma 0 through it, and we can write it gamma mu dagger gamma mu, that is equal to gamma 0 gamma mu. We can define it as gamma 5, that is equal to I gamma 0, gamma 1, gamma 2, gamma 3, that is equal to 0, 1, second row 1, 0. This is the seventh property with the characteristics gamma 5 dagger equals to gamma 5. Similarly, gamma 5 square must be equal to 1, that we have defined the first property gamma 5 gamma mu, that is equal to 0. This is the seventh property. So basically these seven properties shows the how we can define the properties of the Dirac gamma matrices. Now we are going to define the Dirac adjoint equation and the adjoint spinors. Similarly to the case of the Schrodinger and the Klein-Gordon equation, we can also define the current density J mu that satisfies the continuity equation. In Schrodinger equation and Klein-Gordon equation, we also define the current density J mu that can satisfy the continuity equation. First, we write the Dirac equation as iota gamma 0 curly by curly t plus iota gamma dot del minus m multiplied by psi, that is equal to 0. If we open the above equation, we can write it iota gamma 0 curly by psi by curly t plus iota summation k is equal to 1, 2, 3 gamma k curly psi by curly xk minus m psi, that is equal to 0. This is our equation 10. As we now work with matrices, we use Hermitian conjugate rather than complex conjugates and find for the conjugate equation. We can write it as minus iota curly psi dagger by curly t gamma 0 minus iota summation k is equal to 1, 2, 3 curly psi dagger over curly xk into minus sigma k minus m psi dagger, that is equal to 0. This is our equation 11. Here you can see there is the minus sign that disturbs the Lorentz invariant form of the equation. How we can restore this covariance? We can restore Lorentz covariance by multiplying the equation from the right by gamma 0. So using this, we have minus iota curly psi dagger by curly t gamma 0 minus iota summation k is equal to 1, 2, 3 curly psi dagger curly xk minus psi dagger minus m psi dagger gamma 0, that is equal to 0. So using the anti-commutation property, that is gamma 0 gamma k, that is equal to minus gamma k gamma 0, our equation 11 will be written as minus iota curly psi dagger curly t gamma 0 minus iota summation k is equal to 1, 2, 3 gamma sigma psi dagger over curly xk gamma 0 gamma k minus m psi dagger gamma 0, that is equal to 0. This is our equation 12. Now we are going to define the adjoint Dirac spinor, that is psi bar, that is equal to psi dagger psi 0. This is our equation 13. In equation 13, we have defined the adjoint Dirac spinor. Now we can notify that the is the row vector. Dirac spinor can be written as row vector psi1, psi2, psi3, psi4. Adjoint Dirac spinor. We have Dirac spinor as row vector. When we define the adjoint Dirac spinor, the row vector converted into the column vector. We have Dirac spinor as row column vector column matrix. When we define the adjoint Dirac spinor, our column matrix will be written as row matrix, that is psi1 bar, psi2 bar, psi3 bar, psi4 bar. We have defined the Dirac spinor and adjoint Dirac spinor. Now the adjoint Dirac spinor satisfies the equation 12 as minus iota curly psi bar over curly t gamma 0 minus iota summation k is equal to 1 2 3 curly psi bar over curly xk gamma k minus m psi bar, that is equal to 0. That can be written as in shorthand as iota curly mu psi bar gamma mu plus m psi bar, that is equal to 0. This is our equation 14. Equation 14 is the adjoint Dirac equation. In previous we have defined the Dirac equation. Now we have also derived the adjoint Dirac equation. Now we are going to define the current density as we multiply the Dirac equation from the left by psi bar and we multiply the adjoint Dirac equation from the right by psi. Now we can write it as iota curly mu psi bar gamma mu plus m psi bar into psi, that is equal to 0. And if we multiply the Dirac equation from left by psi bar, we have psi bar into iota curly mu gamma mu psi minus m psi, that is equal to 0. Adding up these two equations, we have psi bar into curly mu gamma mu psi plus curly mu psi bar gamma mu into psi, that is equal to 0. This is our equation A. Now equation A satisfies the product rule, that is curly mu psi bar gamma mu psi, that is equal to 0. This is our equation B. As we know that using the equation of continuity, we have curly mu j mu, that is equal to 0. Equation C. If we compare equation B and C, we have current density J mu, that is equal to psi bar gamma mu and psi, equation 10. Equation D. Here there is a note that is written for understanding psi is the column matrix, and we also see that psi bar is the row matrix, gamma mu, that is 4 by 4 matrix. We cannot take simple numbers or variables, so we should take care of order. For example, we will must written as psi bar, because column matrix into row matrix not possible. Similarly, we will write as psi bar psi, that is matrix algebra. Gamma mu psi bar, it is not possible. Similarly, if we write it psi gamma mu psi bar, that is also not possible. Psi bar gamma mu psi matrix algebra works, so it is okay. Now we will find the adjoint equation as iota curly mu psi gamma mu plus m psi bar, that is equal to 0. If we multiply this equation from the left by psi, then it has no meaning. Multiplication of matrices will not be possible. We will need to multiply psi from right side. Now Dirac equation, that is iota. Now we are going to discuss the Dirac interpretation. As we know that we have derived the current density J mu, that is equal to psi bar gamma mu psi. J0 that is equal to psi gamma 0 psi that is equal to psi dagger gamma 0 psi that is equal to psi dagger psi that is equal to summation I is equal to 1 to 4 psi I square greater than 0. Therefore, the probability density is always greater than 0. This is the historical motivation of the Dirac equation. However, we had seen in the Pauli's interpretation that J mu that is equal to rho J was the current density. In that case, J mu that is equal to minus E psi bar gamma mu psi. As we know that it is the 4 vector current density, just we used it before in the Feynman Stuckberg interpretation, the particle solution with negative energy is the anti-particle solution with the positive energy. So basically this is the Dirac interpretation. In next lecture, we will find the plane wave solutions of Dirac equation and talk about the antiparticle spinor. These are the reference books for this lecture. Modern Physics by Mark Thompson, 2013. Quarks and Leptons, an introductory course in modern particle by Helson and Martin. So basically these are the references book for this lecture. Thank you so much students. Starting from the problem related to the Klein-Gordon equation, we discussed briefly about what is the Dirac equation, what is the covariant form of the Dirac equation. So far we have discussed this lecture briefly. Thank you so much.